welcome to our presentation. I see a few people in the audience who were at my last one last year. This is going to be far less mathy and academic than my previous talks. This is going to be a little bit more of a tutorial, as you will. In fact, I hope that this presentation goes up tonight to our website as kind of the step-by-step tutorial on how ROS2 can integrate in with the new PX4 Autonomy Development Kit. So, first off, what are we going to go over today? I want to talk a little bit about ROS2 setup and installation guide, along with the two main ROS interfaces that we've set up for the developers. One of them is MPA to ROS2, which is going to take our underlying inter-process communication and expose data into the ROS2 land. The second is the micro DDS service that Ramon pointed at in his keynote speech, and how we can interface into PX4 UORB topics through that. Finally, we're going to show a nice little demo on how you can start developing with ROS2, and that's how to fly a figure 8 through VIO. And so we'll discuss how VIO data can be pipelined into PX4 through either Mavlink or the new DDS interface. And then finally, a little overview of what it takes to do a nice, smooth, continuously differentiable figure 8 path. So, what are we trying to accomplish with the entire ROS2 integration? Well, in the VOXL SDK and the VOXL ecosystem, we already have an inter-process communications environment set up, all running at a very low level, and that's called modal pipe architecture. We're going to show you how this plugs into ROS2 and gives you full access to all of the data that's being passed around. Secondly, we're going to talk a little bit about how we can pipeline data that's running in the PX4 Autopilot implementation in our sensors DSP, and how that data gets transferred back into the applications processor, and then finally into ROS over that DDS service. For more information about this arrow, so this little data transfer back and forth between the DSP and the applications processor, please see Eric Katzfi's presentation tomorrow at 12:30 in this room. He's going to go way more in depth into that because that is far more complicated than I have time for in this presentation. Okay, so what hardware are we going to be using for this demonstration? Well, this is the drone that Ramon held up this morning at the keynote speech. This is the new PX4 Autonomy Development Kit. And so this comes out of the box with PX4 114 set up, as well as all of the ROS2 demos and the ROS2 environment that we're going to cover today. Just some high-level specs. The reason this is well suited for working in ROS2 and doing high-level autonomy stuff is simply the processing power and the vision capabilities. So you can plug in a number of different cameras to this, but we include out of the box a 12-megapixel IMX412 color high-res camera, which is set up for 4K video streaming, recording, snapshots, all of that. We also include a 1-megapixel global shutter computer vision sensor for doing visual inertial odometry, which is one of the key parts of autonomous drone behavior, particularly in indoor GPS-denied environments, and is going to allow us to do a very, very clean and accurate figure 8 indoors. And I'm actually going to pass this around the room while I am talking, so hopefully everyone gets a chance to see that and see what's going on. Okay, so what ROS version are we going to be using? We're going to be using ROS2 Foxy for a couple of reasons. I know it is technically EOL, but this is still what the vast majority of ROS nodes that I've come across are based on. It's still extremely well supported. It's also a limiting factor based on the system image. So we'll be moving to Ubuntu 20.04 as the base operating system for this platform very shortly, but we were able to get Foxy running on 18.04, which is what it's running today, knowing that we're going to be moving forward to a native Foxy installation going forward on Ubuntu 20.04. Okay, so how do we install ROS2 Foxy on this? Well, it comes pre-distributed with it. As part of the VOXL SDK, a number of software packages are loaded up. The majority of them are actually pre-installed services that are installed and running. However, we also have a number of packages which are physically there on disk as a local Debian apt repository, which means that you can apt install a lot of our packages without needing an internet connection. Many people like to build their own versions of ROS or may want to compile tweaks and have their own distributions of ROS. And so we're not going to force you to use our distribution, but we are going to have it pre-installed, well, okay, not pre-installed, pre-included on the disk. So all you have to do is run apt install VOXL ROS2 Foxy, and it will install. No internet connection necessary. So that's easy. Step one of the tutorial, install it. Second step, just check everything works. I think anyone who's done ROS stuff here knows. First thing, check your environment variables, make sure that everything's being set up. We have our own bash profile scripts to include the opt-ros foxy setup.bash setup script, as well as some of our own nodes that come pre-installed. So those are all native to your bash prompt as soon as you log in. Next step, we're going to look at our VOXL MPA to ROS2 package. So this is the other Debian apt style package that comes as part of the SDK. And this is going to include a few things to save you from having to compile them yourselves. So it's going to come with the PX4 ROS.com node, which is sort of the ROS side of the interface through DDS into PX4 to expose all of the topics that you're going to be interacting with PX4 through. It's also going to include the PX4 ROS messages, of which I think there's like 60 different ROS messages in there, all of which take about 30 minutes to compile yourself if you want to. I'd recommend not. I'd recommend just doing apt install this, and then a few seconds later you'll have all of those ROS messages available. Each of those ROS messages in PX4 messages, by the way, represents a UORB topic, which is internal to PX4. Now, both of these packages are, one, fairly new. I think part of our reasoning behind releasing all of this as part of the SDK is to build up the user base of the PX4 DDS interface and hope that more people will contribute to adding new features in the same way that MavROS and Mav SDK really bloomed as soon as they gained popularity in the community. We wanted to work with Ramon to try and do the same for this DDS interface as we move toward more and more integrated ROS2 compatibility. Next, we're going to have the VOXL MPA to ROS2 node itself. This is our bridge into the modal interprocess communication ecosystem, and I'll go through all of the data types that we have available through there. We also have VOXL messages, which contains one ROS message, the only one that we could not find a sort of out-of-the-box interoperable ROS2 standard message for was our AI detection. So we have, I think, about 5 neural nets pre-installed as part of the SDK. Things like MobileNet and YOLO are all, and PoseNet are all baked into the SDK. And we've made a ROS message to describe an AI object detection. So that is published through ROS so that you can subscribe to detections and where they are within the camera frame. Finally, we have the VOXL offboard figure 8 demo, and that's what we're going to conclude with in a video at the end, which is just an out-of-the-box demo showing that you can take one of these autonomy development kits, run a single ROS command, and it will take off, fly a figure 8, and land back down again. So that is your ROS2 PX4 integration hello world. Okay, so how do we install that? Well, apt install VOXL MPA to ROS2. All of these are distributed as apt packages, which we continually maintain and have online in our apt repositories, but they are also in the local repository. So if you are out in the field and don't have an internet connection, or if like me, while at university, you had this problem of the university internet requiring many, many levels of sign-in and MAC address authentication. You can bypass all of that and just get going until you have a normal internet connection. Then we have a configure script. This, for now, does require an internet connection because it has to pip install some of the extra Qualcomm packages that we needed. Those will slowly make their way into the system image, and that will no longer be a requirement, so it will be completely offline. But so far, for a single line of Python 3 pip install, that step does require internet. The other thing that this configure script does is set up a new script in your profile.d directory, which means every time that you log into VOXL, it's going to load the Foxy environment setup, and it's also going to make sure that the MPA to ROS2 environment variables get loaded up into your environment so that you're good to go. Okay, so once those 3 steps have been completed, the next time that your VOXL boots up, you can simply log in and fire off the MPA to ROS2 node, and it will spit out that it has seen all of these different image, IMU, and pose and point cloud data types, which are available out of the box with the SDK. All of this is running out of the box. So a few things we have here. We have data from the high resolution camera in varying colors and resolutions. We also have QVIO overlay, which is an image stream which is overlaid with feature points in the room being tracked, as well as some data metrics and the location that VIO is showing you the drone is at in space. So this is our kind of visual odometry diagnostic image. We also have, let's say this is the tracking camera, so that's the global shutter camera that's being used for visual inertial odometry. Since it's a global shutter camera, it's extremely well suited for fiducial relocalization, such as Aruco markers and April tags. So if that's something you want to do in your ROS ecosystem, the global shutter images are available there as well. Finally, down here at the bottom, we have QVIO, which is our visual inertial odometry topic, and we actually published that as 2 different topics in the ROS world. I'll get to that on the next slide. We also have these 2. VV Hub stands for Voxel Vision Hub. That is our computer vision and relocalization service running in the VOXL SDK. That publishes 2 poses. One of them is a body with respect to its local frame, and also body with respect to fixed frame if you're using our April tag relocalization service out of the box. So if you don't feel like writing your own relocalization service, you can use that out of the box, and you'll have a pose published in ROSland with April tag relocalization pre-set up for you. Okay, so what are these data types? These are all standard data types for all poses. So that's the VOXL Vision Hub body with respect to fix and body with respect to local poses, as well as the VIO pose. These are published both as a geometry message and a nav message. It's basically the same data. If your nodes are set up to subscribe to one or the other already, you can just pick and choose which one you want to go through. Okay, so now let's look at the PX4 side. So this is mostly copy-paste out of the fantastic PX4 documentation. We've just bundled it up and have it running already as a background service. So as part of running the configure MPA to ROS script, that has also fired off a what we call the VOXL micro DDS agent, which is exactly copy-paste the steps that PX4 recommends for running this sort of thing on a Raspberry Pi, but we've configured it for talking through UDP to the PX4 instance running on the DSP. And that runs in the background, uses very little system resources. It's enabled, you don't have to even know this exists. All of the topics are published in ROS, just know not to disable that service or you'll wonder why things broke. Okay, so now let's see what PX4 is publishing. This is where it starts to get interesting, as we used to go through Mavlink or MavROS or MavSDK to try and access some of the information inside of PX4. But it was a little bit indirect. It all had to go through this mavlink transition. And whenever you go from one data type to another, there is an inherent loss of information. This setup gives you direct access to the UORB topics within PX4. So when you start publishing these, you're basically doing the same job as mavlink receiver.cpp. So when mavlink receiver.cpp in PX4 received a mavlink message, it would just fire off a UORB message of the appropriate topic. Now you can bypass that step and just go and inject UORB messages straight into PX4's inter-process communication. So there's a few interesting ones we're going to look through here. One of them is going to be offboard control mode. So this is how we now tell the MPC or MCP, multi-copter position controller, is it going to feed forward your set points to either position, velocity, or acceleration, or some set of subset of the above. And then to send those in, we're actually going to send in the vehicle trajectories and also vehicle visual odometry, whether you use our VIO setup or one of the many fantastic ROS nodes for doing VIO, that is your choice, but it gives you an opportunity to simply inject these messages straight into UORB, and therefore EKF2 is going to pick these straight up unencumbered by anything else. Also a few useful outputs is going to be kind of the typical things that you would want to look through over a mavlink stream, such as attitude. My personal favorite on here is actually the vehicle status message, because this gives you the full output from the commander module. So we can see exactly what modes PX4 is running in, exactly which sensors are up and running, which sensor checks have passed, which arming checks have passed. That is a particularly useful message to get to. It is the first, I want to call it, thank you very much. I'd rather not go home without that. This is only the first quarter or a fifth of the data in that vehicle status message. That's a very, very handy one to have. Okay, so before we can take off and fly indoors or do any sort of accurate positioning, we need to get some VIO data into PX4. Still two very valid ways of doing this. For the last 4 or 5 years, we have been sending data in through mavlink as an odometry message. However, now we have the vehicle visual odometry UORB topic directly available to us to publish through in ROS, and these are identical. Line by line, these are the same, but you can see the difference in formatting. So this is the typical ROS message format on the right that gets compiled into both the C and the Python bindings. But however you want to send VIO data in, completely your choice, because they're all going to end up as a vehicle visual odometry UORB message anyway. Sending VIO data into PX4 has a little bit of subtlety to it. You can't just take a random VIO node, plumb the data into PX4 and expect it to work. You have to be aware of a few things. One of them is that VIO is IMU-centric. It is only aware of the odometry, aka the distance that something has traveled from where the IMU was when the algorithm started up. And everything is based on where the IMU is. Now, if you imagine an extreme case where the IMU of your drone is hanging off of a 1 meter stick off to the side, and you start rolling left and right, that IMU is going up and down, but the center of mass of the drone is not. And so it's very important to make sure that you do the appropriate set of coordinate transforms to get both the position and the velocity data from VIO transformed into body frame. Now, PX4 can do this for you. It's called the EKF2 EV position X, Y, and Z PX4 parameters. So PX4 can do this offset for you. I personally like to do the transforms myself, because when I'm commanding the drone around, I like to know where it is so that I can run feedback. For example, when I see an April tag, I like to know where that April tag was, not just relative to the camera, but relative to the center of mass. And so I typically handle these transforms myself. All of this math is baked into a package called VOXL Vision Hub, by the way, so you can see all of the source code that we've written to do this, but this is running out of the box just behind the scenes. So this IMU with respect to body coordinate transform, and every one of these blue blocks is a coordinate transform, by the way, and every green block is a reference frame, or if you like, the center of a Euclidean coordinate system. So we like to define the body as the center of mass, and then as part of your config file, we type in where is the IMU with respect to the body. And that's going to include both the offset and also the rotation between them. So if you map things up sideways, for example, or upside down or back to front, we can account for that. Next, we get IMU with respect to VIO. So this is the output from the VIO algorithm. And I just like to call VIO frame as the frame of reference where the IMU was when the drone powered up. So that's where VIO thinks the origin is, because VIO does not know where the center of mass is relative to its IMU. So this IMU with respect to body we get from a config file. That's your job to update if you're setting up a drone yourself, or our job to get correct if we're shipping them. And then IMU with respect to VIO is the actual output from VIO. This is what VIO is telling us is the distance we've moved and what our current orientation is. I also like to define another coordinate frame, VIO-GA or gravity aligned. Not all VIO algorithms will align the wheels with Z down aligned with gravity. Some will start crooked, and that's it. It thinks the world is at 45 degrees, where up and down is actually like this. However, they will still estimate where the gravity vector is with respect to that VIO coordinate frame. And so if you take the cross product between 0, 0, 1 with Z pointing down and the gravity vector, you can get a nice angle to rotate the entire VIO frame back level with gravity again. So that's good to be aware if you are trying to use one of the many open source ROS nodes for VIO. It's good to check. If you start your drone crooked on its side, does it actually know that gravity is not straight down, and is it estimating a gravity vector for you? Finally, if we multiply all of those coordinate transforms together, we can finally get body with respect to local, which is what you want to send into PX4. Let EKF2 have an easy time in life, give it exactly where the center of mass is, and then you know if you're trying to log or keep track of one set of XYZ positions of the drone, you know you're across the board just looking at the center of mass. Okay, so now we've got position data going in, and we've got PX4 status coming out, and we have a way of telling PX4 what to do. Now we get to decide what to do with it. I really like the figure eight because one, it is smooth, it's continuously differentiable, and it doesn't take up very much space. You can do it in a small room. It also stresses VIO quite a lot because the camera is yawing and sweeping around the room very, very quickly, and so it's a good stress of your camera's shutter speed and clarity. It's a good test of feature tracking, and it's also a very good test of the feedback controller that you've got the drone tuned to, because it needs to follow a very tightly yawing path, and if you have any overshoot or oscillation in your feedback controller, you're going to get a lot of obvious wobble. And so I will spend a lot of time doing figure eights and dialing in PX4 tuning parameters until it looks just so. So that's what we're going to try and achieve. I really like Bernoulli's lemma skate for this. Some people will do a piecewise version of the figure eight that's basically two circles next to each other. I like Bernoulli's lemma skate because it crisscrosses in the middle at orthogonal angles. So this means that the drone is going to take two different paths over the center, and if you have a nice big fisheye lens that can see the ground, that lets your feature tracker crisscross over the same area from two different angles, And if you're doing it something like ORP-SLAM3 with relocalization, this is a good test of the descriptor matching to make sure it can pick up those same feature points as it goes back over from different orientations. I've posted up here one little QR code, and also at the end I have a URL to go to a link I've generated from Wolfram Alpha that has these equations listed out there. These equations are also copy-pasted into both C and Python examples that I've linked at the end so that you can see how this is evaluated into creating the position, velocity, and acceleration set points that are going to go straight into PX4. By the way, if you do have an equation like that, even if you went to grad school and have a degree in math, I trust Wolfram Alpha to do my differentiation for me. So I've allowed Wolfram Alpha to do it, and sure enough, it works fine. Okay, now how are we going to tell PX4 how to fly? Well, a couple of options. The way that we've done everything in the PX4 community up to this point is with mavlink messages. So it used to be the mavlink set position local ned t struct, and that was the message that we sent in. That had position, velocity, acceleration, as well as a yaw and a yaw rate, plus a type mask. Now, the type mask is a bit mask saying whether PX4 should read the position, the acceleration, the velocity, or a subset of those. It is very important if you are going to forego velocity and acceleration set points and only give position set points that you set the type mask appropriately. Otherwise, the feedback controller in PX4 is going to be trying to follow your position set point, which requires a non-zero velocity and a non-zero acceleration, meanwhile trying to keep zero velocity and zero acceleration, which is going to have a very wonky flight path. Where possible, it is always good to feed forward known values to feedback controllers, because feedback without feed forward requires an error to be present before it can apply any actuation. That means that if you're only sending in a position set point to PX4, if you want it to move forward, it will not start moving forward until after the position set point is always ahead of the actual drone's position. Now, under steady state, the integration term in the position and velocity controller will eventually catch up. But if we're trying to do very precise indoor maneuvers, such as navigating through a pile of boxes or through a doorway or a window, you need as much control as possible. And so that's why I like to pick the continuously differentiable path to fly, because then we can let Wolfram Alpha figure out what the feed forward terms are for velocity and acceleration, and off you go. Okay, so just from the coding standpoint, since we're doing a repeating loop, divide up a certain time slice. I think our time slice was like 8 seconds to complete the whole thing, was pretty reasonable. I've done 4 seconds before. It's pretty fun to watch, but I wouldn't like stand right next to it. It's very easy to code up just an array. So if we want to send a position set point every 50 milliseconds or so, which is pretty reasonable, then create an array of set points, pre-fill them ahead of time. That way you have very little work to do in the loop, and you can stick closer to a real-time loop sending those position set points in. Okay, final thing we're going to do before trying a ROS figure 8 is turn off the MPA figure 8. So all Modal AI products come with the figure 8 enabled out of the box so that you can hit a switch on the radio and do the figure 8 as soon as you receive the product. Please turn that off. PX4 will not be happy if you have 2 simultaneous sources of set points conflicting with one another. And once that is going, you can do a figure 8. So also big credit to Zachary Lowell and everyone else at Ascend Engineering for helping put this demo together. So this is going in HIDL and actually takes the Modal AI MPA demo one step further and includes the ROS2 commands for taking off and landing. So this really is a Python 3 ROS2 hello world for doing offboard control with ROS2, including takeoff, checking system status, checking the flight mode if it's gone into off-board mode or not, and landing. So we can also do this live. So I'm going to fast forward maybe a little. No, that's a fun video. So here we're going to see on one of our other drones, just checking that VIO is holding very, very well by pushing it around the room and letting it hold still. And for this, I set up a little tweak to the demo where instead of having it do the figure 8 in place, wherever the user hit the switch, I had it always do the figure 8 back in the middle of the room so that I could send it 5 meters up to the corner of our ceiling and then hit the button and see how it reacted, suddenly having the set point move all the way down and then drop into a nice smooth figure 8. So this is now something that all of you know how to do and can do out of the box, and all of the code to do it is here. So this presentation will be available for download after the conference, and you can also find everything at docs.modalai.com, but all of the source code shown here is part of the SDK as of last night nightly. We rushed to get everything ready for you guys for this conference. Along with all of the equations, more documentation about the DVDF's interface, and a couple of the excellent examples up there. Arc Electronics has a great example as well that you should definitely check out as another reference for this. And I am about out of time. Do we have any questions? Nothing? All very, very clear? This is all built for ARM64. Yep. Yeah, this is all running on a 8-core Qualcomm ARM64 chip. Anything else? Quiet group, I must have bored you. The hotel will not let us fly. We had this same problem last time. Because it's a figure 8, it only takes up like 2 meters of space, so it's very small, it's very safe. But the hotel shot down our request to do a live demo, I'm afraid. But if any of you guys come to AUVSI coming up soon, that's going to be in San Diego, we will be there with a net and we will be flying. Yeah. I have not tried anything beyond this, but yes, all of that is absolutely possible. There are path planners and polynomial evaluation things available in ROS. All of those you can plug into those exact same DDS topics and off you go. Yep. I just wanted this to be kind of a hello world, very simple, like, hey, evaluate these 2 equations and plug it in here. Cool. Well, if that's it, enjoy the rest of the conference. If you have more questions or want to chat one-on-one, we are at booth P1. Thank you very much.